here is the same, actually, as this. Because whether you write the sum of I squared from 1 to n or the sum of k squared from 1 to n, it's the same thing. It's 1 plus 2 squared plus 3 squared plus dot, 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 plus n squared. It's the same thing. So I can use this magical formula that I haven't proved over there, which you could prove by something called mathematical induction. And I have done that in previous Calculus 1 classes, but I'm not going to do it to you guys. Like that. So now to calculate the area, all we have to do is take the limit as n goes to infinity. Because this is the right endpoint rule for arbitrary n. So I'll write it over here, the integral from 0 to 2 of x squared dx is the limit as n goes to infinity of r sub n, but we just calculated r sub n as this. I'm going to go ahead and divide through the n cubed. All right, what I've got is, I've got 8 over 6, and that gives me 1, well, I'll write it this way, n over n, n plus 1 over n, 2n plus 1 over n. All right, so that limit, I've got 8 over 6. We could write that as 4/3, right? 4/3, and this goes to 1. And then we've got 1 plus 1 over n, and then 2 plus 1 over n. And as n goes to infinity, the factors there, they go to 1 plus 0 and 2 plus 0, so the limit is 8/3. Now, so I'm showing you this because I want you to understand that we can actually do these calculations for like polynomials, right? But for anything except for polynomials, these kind of calculations are pretty much hopeless. Like it's very fortunate that we know these formulas and we can actually do this. If you try to do this for like sine, it's hopeless. We don't have formulas for like adding sums of sines and things like that. Well, maybe an expert in trigonometry might, but are we experts in trigonometry? We are not, right? So let me, spoiler alert, tell you the fundamental theorem of calculus part 2 again. It says that the integral from a to b of f of x dx is equal to f of b minus f of a, provided f is an antiderivative of little f. All right? So just to complete the thought here, even though it's, we haven't proved this yet, and I don't really have the right to tell you it in some sense, because, we haven't, we're going to prove this week, all right? Probably tomorrow. So let's put this into practice. How about for our example, integral from 0 to 2 of x squared dx. How do we do it? By the way, notation for this is just f of x, and then you do bar from a to b. Like that's a notation for that difference. So what's the antiderivative of x squared? It's 1/3 x cubed, right? 1/3 x cubed, 0 to 2. So that gives me 2 cubed over 3 minus 0 cubed over 3, also known as 8/3. And while we're at it, let's do the earlier example we did today, which was what? The area from 1 to 3, right? Of x squared plus 1, wasn't it? So to calculate that area using the fundamental theorem of calculus part 2, we just need to find an antiderivative for x squared plus 1, which is what? 1/3 x cubed plus x, evaluated from 1 to 3, right? So that looks like 1/3 of 3 to the third plus 3 minus 1/3 of 1 cubed plus 1. So that gives me 27, 27 minus 1, which is 26/3 plus 2, which is also known as 32/3, which of course is the answer we found, with the help of Wolfram alpha, mind you, to calculate the pesky details of the sum. Obviously, fundamental theorem of calculus part 2 is the way to go on these, right? Which is better? Calculating limits as the number of boxes go to infinity directly, or using this beautiful and wonderful, nearly magical theorem, really? Obviously, the theorem's better. So, I think we have time for one last thing. And so this is kind of an oddball just a fun thing, right? And when I was homeschooled, and we went to a curriculum convention at some point, and this random guy came up to me, and my brother, and he's like, calculus, it's all about how to find a circle, and you divide it up into triangles and show that the area. And I'm like, what are you talking about? Well, here's what he's talking about. So if we take a circle, and we wanted to calculate its area, you know what we could do? We could divide it into a bunch of triangles, right? And what would the area of these triangles be? Suppose we do the triangles of equal angle, So these are the sectors. I mean to draw these sectors so that they have the same theta. So I want theta, let n be the number of triangles, right? So then theta is 2 pi over n. And I want this to be radius r. So if that's radius r, what is the formula for the area of a triangle? If I know that this, area is 1/2 r squared sine of the angle, right? This is a formula that we learn in trigonometry, that if you have a triangle, if you have two adjacent sides and the angle between them, the area is 1/2 sine of the 1/2 the product of the sides times the sine of the angle between them. You could also derive this formula in other ways, but that's true. Now that's just the formula for one of them. So what's the total area then? This is the area of just one of them, So the total area would be n, right? R squared sine theta over 2. Because you just have to multiply the area of 1 times n, right? But check it out. What is that? That's r squared over 2 times the sine of 2 pi over n, divided by, 2 over n. I'm going to say 2 pi over n, and put a pi up here. I did something wrong. Rats. It's not working out quite right. I did something wrong here in the setup. I'm not sure if it's the... Oh, maybe that's it. Maybe I just need to... Let me stick with the r squared over 2 and the... I'm sorry, guys. I should have tried to waste 10 of your minutes rather than 3 of your minutes on this. Our time's up. Anyway, if you keep working on this and you don't make whatever mistake it is, maybe there's no mistake. Maybe it's just this limit is subtle. Yeah. This will work out to pi r squared. I've done it before. Like it basically rests on the fact that the limit of sine h over h is 1. Like that limit comes into play. But if you know that, you can. It's enough to prove that the area of the circle is pi r squared. But this is very different than what we're doing in here, right? This is, and yet it's the same, right? Taking the shape of the circle and dividing it up into triangles, letting the number of triangles go to infinity, that should calculate the area. So, sorry, I messed it up today. I better stop there, though. Oh, and